Battle 2, fight. Okay, so we're continuing our talk about pressure. We just kind of did an intro to pressure, and our last thing that we saw was that a change of pressure, so delta P, is equal to rho, the density of the fluid, g, the gravity of the planet you're on, like Earth, 9.8 meters per second, and then delta H, where delta H is like the depth or how far you are from the top to bottom of your object. And it's important to remember it's just the top to bottom of your object because it's kind of a weird idea. This delta P, when we're thinking about it, if our water's up here, and let's say I put a box deep underneath the water right here, okay? If I asked you the question then, what is the difference in pressure from the top of the box to the bottom of the box right there? What is the delta P? You should never then go from the top down. You actually don't need to do that. What you need is the delta H right here. This is actually what you need because, there is some pressure on the top of the box due to all of this water above it, but the water on the bottom is also acting on that box as well. And the really cool thing about pressure is it is acting up, down, left, and right. So when we think about delta P, you only want from the top to the bottom, or from like one position to the next. So if I did ask the question, what is the difference in pressure from the surface of the water down to, the midpoint of the box, yeah, then you would need this entire delta H. But it really depends on what your start, what your finish is, and what your difference that you're finding. So that's one of the ideas of pressure there. One of the other weird things about pressure is because it does act up, down, left, and right, and it does this equally. When we're at the bottom here, while we do have so much water above us pushing down, that water is also like kind of pushing us up in a way. And it's also pushing, on the sides of these boxes. It's pushing everywhere in every single direction. There is a pressure, or there's a force acting on this area of the box. So kind of a weird thing to think about, but pressure is acting in every single direction on an object. And we'll actually use this idea in a little bit to allow our objects to have an easier time to float, to have a buoyant force whenever we get there. So it is important to remember that pressure is acting in every single direction. It is a scalar, not a vector, but it is in every direction here. It is also important to remember, and this is super, super weird, so like put a star next to this, where if we have, and maybe I should kind of redraw this here. We'll redraw our fluid box. We'll do it as a perfect square. Give me a rectangle. Whoosh. If we have our fluid box here, and we look at the side, while fluids, the pressure from them is acting in all directions, a pressure cannot act any direction but normal to a surface when it is in contact to the surface. So the pressure can only act in this direction here, such that it is 90 degrees or perpendicular from that surface of contact. And that's kind of like a weird rule, but let's think about why that has to be. If for some reason your pressure here was pointing up, then what this would mean is that the tiny bit of fluid that would exist right here, if there's a little bit of fluid right here, that would mean that there's a force acting upwards on that fluid, which means that this fluid wants to rise or move upward, which means that if we go to the top of our box, let's say our fluid level only comes to like here, all of a sudden the fluid's like, I'm out of here, and it's just going to rise up the side of your glass. I've got a thing of tea here. The fluid's not just racing out and spilling over. That's not a thing. Same idea with like, it can't be going at some arbitrary angle, because if we broke up that vector, some of it would be pointing up. We also can't have it, pointing down in this case, because now your fluid's just going to keep compressing itself. That doesn't make any sense either. So fluids are going to act with their pressures perpendicularly to a surface of contact. So that's a very important idea there. One that doesn't pop up often, but is a fundamental idea in the world of fluids. Now, when we think about pressures and what are some use cases of pressures, how could we use them with this janky handwriting here? We can use pressures to apply forces to cause objects, or fluids rather, to move. And one of the key pieces of thinking about this is thinking about the difference between a low pressure and a high pressure. If for some reason you had a scenario like, I don't know, maybe you've got a cup full of tea sitting on your desk and you'd like to show what pressure can do, well, we could do this. So here is a cup full of tea, and I've got a nice little straw here. And if I wanted to, I could simply, take my lips, put them to the straw, and I could sip up that yummy, yummy tea. Just sip, sip. So good. That's a day-old tea right there. It's been sitting in the room for a day, so I could do that demo. Anywho, what is actually happening? How do straws actually work? A lot of people think that whenever you are using a straw, you're using suction to like pull the liquid up. And the more you suck, like the more suction you have to pull up that liquid. But that's not actually what's going on. What's going on is the following. Whenever you have a cup like this, there is some fluid in it. Let's just make it water, but it could be, any fluid you want. Whenever you put the straw in, straw, 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 straw. When you put the straw in and then you actually suck up, what you're actually doing is inside your mouth, you are creating a low pressure. And when I say low pressure, what I mean is that this low pressure here, well, it's less than 1 atmosphere. And why does that matter? Well, the pressures want to reach an equilibrium. And what's going to happen is, because this is less than an atmosphere, the actual atmosphere that we exist in is going to push down on the fluid. The atmosphere is going to push down on the tea. This is at some high pressure right here. Because it's a high pressure, it's going to push down on the tea, and then it's actually going to push it up through the straw so that it can reach the low pressure, and then it gets into your mouth. Ta-da! This is why, if you've ever used, if you ever like had a system that wasn't opened on the top here, so I can like stick my hand in the tea, sometimes you can't actually suck anything out of the straw. And why, if whenever you're a small child and you're drinking out of a bottle like this, a lot of children, when they start drinking out of bottles like this, they put their whole lip around the entire thing. They drink like this. And they start having to like crush the bottle. They can't drink as much at some point. Where whenever you're an adult, you leave a little bit of a gap. You're like, and the reason you left the gap there was because you're an adult, you're a genius. The atmosphere is actually able to go inside the bottle, and it's allowing it to push itself out. If you seal this off, you're not allowing the atmosphere to do that, and at some point, you create a low pressure here, which is, keeping the liquid in there. So just some pressure ideas that occur. This also influences how high we could actually pump water. If you're trying to like drain a mine, right? You got a bunch of water underground and you need to extract all that water so you can access the mine. You can only bring that water up so high, because if you're using the actual atmosphere, the high pressure, the 1 atmosphere here, to actually push the water up, if you made this low pressure all the way down to 0, that still designates a specific height that is the maximum you could ever lift the water out of. There would be no way to lift the water any further beyond that maximum, even if the pressure was 0, just because you don't have enough of a push from your high pressure of 1 atmosphere here. So that's just another thing to think about. Sorry about that. Just trying to drink water. But what we see here is that, we have some high pressure pushing on the water, pushing it back up into the low pressure environment. And there is some maximum height we can actually get the water to based off of that. So just kind of a cool thing there. Because of this, we can actually, if we think about the pressures all the way down here at the bottom, we actually have 2 pressures going on. We have the pressure from the atmosphere, and we have the pressure from the water itself. So it's important to think about the two different pressures that we have. And this brings us into this idea of a gauge pressure. So a gauge pressure, if I could write correctly, a gauge pressure, G-A-U-G-E, pressure. A gauge pressure can be thought of as this. If you go out to your car and you deflated one of the tires, what would the pressure inside one of the tires be? Like if you completely deflated a tire, what would that pressure be there? So if you have an uninflated tire, what would the pressure be? Well, you would think that there'd be no pressure in that tire, right? Like it's deflated, but there's still an atmosphere around you. There's still air in that tire, just not extra air. It's just the atmosphere worth. So this is 1 atmosphere worth of air. When we inflate the tire, we add some extra pressure in. The total pressure is then 1 atmosphere plus whatever extra you're putting in the tire. This extra air is what we refer to as the gauge pressure. The uninflated, this is your atmospheric pressure here, okay? Your ATMs. The gauge pressure is anything extra that you're putting beyond that. So if you wanted to find the total pressure in something, your pressure total is going to equal the pressure from the atmosphere plus your gauge pressure. And this means that if we go back and we consider our water scenario, up top, we have some pressure from the atmosphere, but down here, this gauge pressure to the bottom of this container, this gauge pressure, PG, well, that's equal to the rho G delta H. That is a gauge pressure right there. It's really a delta P from the top to bottom. But that is a gauge pressure that we have. So it's important to recognize that just because you're sitting here on Earth and you're not underwater and you don't feel a pressure on you, there is a pressure on you. You've just evolved to get used to it. It is exactly 1 atmosphere, 1.01 times 10 to the 5th pascals. But the gauge pressure is anything extra, and the total pressure is the entire pressure that exists. This is actually very important when you're designing things to withstand certain pressures, because if you just design it to map out the gauge pressure of the depth of water and you don't consider what's above it, then your structure might be a little too weak. And this really comes into play with things like dams and whatnot. Okay, so that's the idea of a gauge pressure, how pressures in general can push from high to low pressures, and they will go from high to low pressures with the push of the force, and what we can kind of use them for. In our next video, we'll exploit some of these ideas of pressures, forces in areas, high to lows, and we'll see how we can use it for a mechanical advantage system for Pascal's principle. But until then, try your best not to get water up your nose, and adios, take it easy.